So I took the liberty to modify a little bit the title of my talk, inspired by Francesco Visani yesterday, and I kept the copyright. And somehow I think the meta creation does sound much better than double beta decay, and maybe we can compete with our dogmatic colleagues in how sexy our titles are now, from now on. Okay, so it actually resonates very well, I think, with my probably rather simplistic view on double beta decay, because to me it's just a lepton number violation generation. And you can plug basically any lepton number violating physics in here, and of course it can be due to the light Majorana neutrino mass, but it can also be due to many other different lepton number violating mechanisms. So the idea of topological detection of the matter creation or double beta decay stems from this inspiration, so from the fact that we want to be as open-minded as possible as to what exact mechanism the nature chose. So the idea here is actually to detect explicitly these two electrons emitted from the double beta decay isotope using a tracker immersed in a magnetic field, so you can reconstruct electron tracks and then detect two electrons, their time of arrival and the energy with the segmented colorimeter based on plastic scintillator. And there are a couple of things which are, there are a couple of implications for that, right? First of all, you have an isotope flexibility, but it also can produce a very strong background suppression by using the particle identification, characterization, and timing. And it may, if you find this process, gives you the ability to disentangle the underlying mechanism. So you can see that if you detect these two electrons topologically, then you really can actually distinguish them from competing processes from the background. And as a result, it can really give you very, very low background indices. If you do detect this process, then you may be able to disentangle the underlying physics mechanism behind it. So the two examples here show you two mechanisms. One is driven by the Majorana mass and the other one by the right-handed currents. So if you look at this, so the plots on the left show the difference in energies between two electrons emitted in the decay, and you can see in blue are the theoretical spectra, and in yellow are the spectra folded with the detector effects. And you can see they're very different, and likewise the angular distributions are very different as well. So NEMO 3 is an experiment which actually stopped data taking quite some time ago, but still produces, as you will see, results. And it was located in the Fréjus underground laboratory, which is the deepest underground laboratory in Europe, 4,800 meters of water equivalent. And it was a detector which was comprised of 20 wedges, or 20 sectors, and each sector, if you remember this conceptual cartoon, you can understand what it is here now. This is the source foil of an isotope, and on either side you have the tracker detector. It's all immersed in a magnetic field, and then the plastic scintillator colorimeter. So these 20 sectors were loaded with 7 different isotopes. You can look for the double beta decay of several isotopes at the same time. And you can understand the power of this method when you look at this spectra and compare it with the background, which is almost invisible here. So what's shown here is the total, the summed energy of two electrons emitted in the beta decay. And of course, the important thing is that you can also detect the single electron energy distribution and the opening angle between them. And for example, by studying this, we've concluded that the so-called single-state dominance model is the one responsible for the molybdenum transition to neutrino decay, to neutrino transition. Okay, so the biggest isotope in NEMO 3 is molybdenum 100, almost 7 kilograms of it, and the result, of course, is now surpassed by other experiments. But if you bear in mind that it was obtained only with 7 kilograms of isotopes. This is quite an interesting result by itself. And of course, there are some other competitive constraints and new lepton number violating physics parameters which we obtained with this result too. Importantly, for future experiments which may employ the double beta decay isotopes with high Q beta beta values, there is no background at all above 3.2 MeV, which observed in NEMO 3 after 5 years of running. So as I said, the results, the results still keep coming out from NEMO 3. There are a few updates on 3 particular isotopes. I wanted to draw attention to a couple of them. So this publication, the neodymium result, was used modern techniques, the boosted decision trees, by using different observables which are available in NEMO 3 detector. It's not just the single energy deposition from 2 electrons, but also the angle and the individual electrons and a couple of other things. And that allowed to increase the sensitivity by 20%, which incidentally corresponds to 1 extra year of running. And another interesting result, which may raise some eyebrows here in the nuclear community, is that we published the results for calcium-48, which is currently in some tension with the shell model nuclear matrix element for the 2 neutrino, for the 2 neutrino decay. Okay, so this is a summary of 2 neutrino double beta decay results, and you can see this all 7 isotopes in all cases are they basically the world's best, world's most accurate measurement of the 2 neutrino half-life, and of course we all know how important they are, and we've discussed it already quite at some length. Okay, so probably the news of the year was our recent publication in the PRL this summer. If double beta decay was not enough, here we go, quadruple beta decay. There are several models in which the lepton number violated by 4 units, and those are the papers which discuss those modules. This is actually, interestingly enough, is only possible, at least within these models, for Dirac neutrinos rather than for Majorana neutrinos. And in this case, you can see the signature of 4 electrons emitted from a single point. Now, the Q values for this process are very small, and the only realistic way to do it directly is by directly absorbing the electrons emitted in the decay. We searched it in a particular isotope, again, because of the Q value available, and our expectations was almost 0, and we didn't see anything, so we put the world first limits on this process. Okay, so NEMO 3 inspired essentially SuperNEMO, this topological detection approach. And the main the main goals of SuperNEMO are listed here. So using this technique to yield a zero background experiment in the first so-called demonstrator phase, to prove that a 100 kilogram scale experiment using this technique, topological reconstruction technique, can reach 50 milli-electron volt neutrino mass scale, and then to explore the feasibility of scaling up this technique beyond 100 kilogram, and I will say a few words about this at the end. And of course, in the event of a discovery by any other experiment, this approach is extremely appealing, not just as a smoking gun for this process, but also to attempt maybe to measure multiple isotopes and reconstruct and maybe even characterize the mechanism, the underlying mechanism of the decay. So SuperNEMO is not just a bigger version of NEMO 3, it's supposed to be a better version, and the main improvements are listed in this table over here. So the main challenges are improving the contamination of the source foils, quite dramatically improving the content of the radiant inside of the detector, and also improving the energy resolution of the colorimeter by a factor of 2. And 2 out of this task have already been, the colorimeter has been demonstrated. I will show you a slide about this. And the second one is partly demonstrated as well, which is one of the most critical tasks. Again, I'll come back to it in a minute. Okay, so the demonstrator module, as you can see, functionally is very similar to DEMOS 3, however, has a different geometry. So it has the source foil in the middle, surrounded by the two tracker modules, which are filled with helium mostly, with some quencher and a little bit of argon, and then followed by the segmented colorimeter walls. It's immersed in a magnetic field again and surrounded and will be surrounded by the passive shielding. The important point is that the full SuperNEMO is a very straightforward extrapolation from the demonstrator because of the modular design. We're aiming at the zero background in the demonstrator phase, as already said, and those are our numbers, the number of events which we expect at the standard exposure, which is the 17.5, 2.5 years of running. Basically, you can see that the sum of all the radioactive backgrounds will contribute more or less equally to the neutrino double BD decay tail, and the expected background in that region of interest is 0.4 events. Okay, how you do that? Well, we embarked on a very aggressive program, radioactivity program, with a two-pronged strategy. One is the background reduction using the assays, and the other one is using the topology and timing to reject those. As one of the examples, radon is one of our key problems, so we've developed two lines of two barriers, two lines of war against radon, so to speak. So we developed a cold charcoal trap, which removes basically the radon completely from our main working gas, from helium, down to the ridiculous levels that even we cannot measure it. We also developed a so-called radon concentration line, following the footsteps of our colleagues from Max Planck Institute, but maybe a slightly simpler version of it. And it has a sensitivity for the large volume of gas at the level of few microbecquerel per cubic meters. So with our purification system, we see nothing in helium there. And there are other things as well. One thing I wanted to mention is a dedicated so-called BIPO detector, which is installed in Canfranc. That is the dedicated detector to measure very, very small contaminations in the source foil, right? So a germanium detector is not very suitable for this kind of levels because the levels we're talking about are 10 microbecquerel per kilogram and 2 microbecquerel per kilogram for bismuth-213 and thallium-208 respectively. So this proved to be very important for our low background program. So the tracker has been produced using a wiring robot, semi-automatic wiring robot, which is shown here. So you build the individual Geiger cells in so-called cassettes, which are shown here. There are 16 cells in this cassette. And then you insert this into a quarter tracker. Basically, this is, if you remember, one tracker module on one side of the foil. So this is half of it. So you're fully populated with the cells. And then we run at the sea level. We run the cosmic rays to commission and make sure that it's all working. The resolutions are there, and the electronic performance as expected. The very important point I wanted to emphasize is that we use the radon concentration line to measure the radon content actually still at the sea level before we go underground of a fully instrumented tracker with everything inside it to see that we actually reach the target of 150 microbecquerel per cubic meter with a reasonable flow rate through the detector of the fresh gas. So these are some pretty pictures how the tracker was living. The tracker was built and assembled in the UK and then left for France and then installed in Medan. All tracker has been delivered to LSM, and we even got into the Guardian somehow at this point. Another very important development was the improvement of the colorimeter resolution. I already mentioned that earlier. So that's actually a major breakthrough, and we really worked very hard with the scintillator manufacturers directly, and also with Hamamatsu, our photomultiplier supplier. And so the results of this very intensive R&D is summarized in a recent paper which just came out, And you can see a summary of the improvements of this, what particular components contributed to the improvement of the energy resolution. At the end, for a plastic scintillator, achieving an energy resolution of 1.8% sigma at the Q value of selenium is a remarkable result. The important thing that this performance has been achieved not in the lab, not on the test bench, but it was achieved in a full production because all colorimeter modules have been produced now. As you can see here, you produce them and you populate the colorimeter wall with it. Okay, so a couple of more pictures of the assembly process of the demonstrator construction. So you can see how this is populated, and this is the full colorimeter wall now populated with the optical modules. So the two quarters, of the tracker you saw previously, this is a panoramic picture, are connected together, and the colorimeter wall is coupled with the tracker detector. So all detector models have now been delivered on the ground in LSM, and half of the detector, which is a colorimeter plus tracker, is fully integrated. We've started the commissioning underground with radioactive sources and absorbed the first tracks in coincidence with the scintillator in the tracker detector, so we can reconstruct actually the individual hits and the tracks themselves. So the heart of the detector, so-called the source foil, has been produced. You know, this is the foil production is now completed, and so this is the selenium-82 is our baseline isotope, as you know, but we continue in R&D on two very interesting isotopes, particularly neodymium-150 and calcium-48. So the current status is that the detector integration is actually happening now as we speak almost, and it will be complete by January. We actually wanted to do it before Christmas, but we don't want to rush it before the Christmas break, and we start running for physics in early 2018. Our simulations show that it will take us only a couple of months, probably less than that, to measure the bismuth in the foil and the radon at the required level. It will take a little longer to measure the thallium-208, about a year. And this target sensitivity will be reached in 2.5 years of physics running. So this demonstrator will be a very important input to future tracker color technologies and to SuperNEMO, of course, as well. So one event I wanted to point out, there is a SuperNEMO inauguration, which is happening actually very soon, on the 9th of November. So if you are interested in coming along, have a chat with me at lunch. Okay, so what happens next? Of course, demonstrator is now our main focus. What happens next? In principle, the original idea was to have 15 to 20 modules, depending how much isotope you put in a single module in there. And in principle, because of the modular design, you can have a distributed location even in different underground laboratories if you want to. The construction can also proceed in parallel, but of course the key question right now is the underground lab space. Now we started thinking about, as I said, there is a R&D, active R&D on the high Q beta-beta isotopes as well, and we also started thinking about what we can do to optimize the design of such an approach to reduce the cost and possibly extrapolate the greater than 100 kilograms. And the last few minutes, I just quickly say a few words about that. So the ideas we've been discussing, actually we discussed it some time ago, but then it was mothballed at some point, is to replace the individual modules with the scintillator bars read out by much cheaper 3-inch PMTs. And if you do this, actually you can sacrifice your modularity by making actually one big module and sharing one wall of the scintillator between two source faults. It will become a little clearer in the next slide. So one question we already addressed a few years ago when we were considering this design is the energy resolution. It turns out that you can achieve the energy resolution with these bars, which is similar to what we have achieved already with the scintillator blocks. So the idea of this compact design is roughly sketched here. So this is a top view. So basically what you see is you have effectively a single module here, and the black lines are the source foils, and it's a top-down view right now, and the scintillator bars, as you can see, one plane of the scintillators is looking now to the left and to the right to look at the events from the foils. This 4-pi enclosure turns out to be, at least from naive simulations, or fairly naive simulations, turns out to be very efficient in catching gammas, extremely efficient, almost 100% efficient in catching gammas, and therefore even identifying positrons without the magnetic field by catching the 511 keV annihilation gammas. The gist of the message here is that not to make a detector which performs better than the current demonstrator, but performs at the same kind of level, but is a small fraction of the cost. So to give it into perspective, so this is the roughly the cost of the baseline design, the demonstrator, right? So when compared or normalized to the cost of the isotope, this is the metric we chose, right? So the metric we chose that the detector cost should not exceed the isotope cost. Instead of 250 kilogram so 250,000 euros per kilogram of isotope, that's the cost of the detector per kilogram of isotopes, this compact design gives you a factor of 5 potential saving. And there are possible other options there to reduce it even further. Okay, so that brings me to my last slide. The topological approach to double BD decay detection remains to be unique, and I think we need to do everything we can to explore the possibility to use this technology and scaling it down to the lower masses as much as we can. It actually is something I didn't mention, but it has, because some papers will still come out from NEMO 3 regarding this, it has a rich physics potential outside the double BD decay. You saw the quadruple BD decay result, but there are also interesting things you can do with Lorentz variation, bosonic neutrinos, and so forth. So what we're trying to achieve here is to see, and here the demonstrator data will be very important, that the topological reconstruction of the double BD decay can, in principle, or we're trying to prove that, right? So eliminate all the backgrounds apart from the 2 neutrino double BD decay tail, right? And this is a much more comfortable background to have, because you have huge statistics of it, and you can characterize it really with exquisite precision, unlike unknown backgrounds for which you have very low statistics and you cannot characterize them very well. So at some point, these future large detectors will be limited by systematics, and you rather sit on something which you really understand very, very well. And of course, there is an active R&D on the high QBT beta isotope, on their separation techniques, and in case of a discovery, as I already mentioned, this is the best way for full characterization of Neutrinoless double beta decay or the creation of matter, copyright Francesco Visani. And I spare you 50 seconds. Thank you very much.